So far, we have been talking about subatomic particles and atoms, and even atoms coming together to actually form molecules and formula units for ionic compounds. But this discussion, this particular chapter, is all about molecules and ionic compounds reacting with each other. And so this is where we start actually doing chemical reactions. So we're getting into chemistry, which is exciting. Um, but there's some additional math that has to be taken into account as we get to this bit. So dimensional analysis will be your best friend. If you didn't get it so well when we were going through chapter 1 and 2 material, go back, review that material because it'll be very important. I want to say this in my videos. Whenever you're doing dimensional analysis, follow your units. If your units work out, you will almost always get the correct answer. So let's jump into today's topic on chemical reactions. So this right here are a few different ways to represent chemical reactions. This top bit up here is a pictorial way. So what we're doing is we're showing a cartoon where we've got a methane molecule indicated by these little ball and these space-filling models here. See that the little black ball in the center, those are carbons. These white balls are hydrogens, and these red balls are oxygens. So if we have a chemical reaction, one of the ways to actually show that is by these space-filling models. But this is not the traditional way. The traditional way to show chemical reaction is down here, this detailed, or rather not quite as detailed equation, chemical equation. And notice left-hand side we have these two different molecules, right-hand side we have two different molecules. Anything on the, and then in the middle there's this arrow. This is called a reaction arrow. Okay, things on the left-hand side of the reaction arrow are called reactants. Things on the right-hand side are called products. And so what we're saying is we're taking a methane molecule and two oxygen molecules and making one carbon dioxide molecule and two water molecules. Now notice if we show up here in the picture, we have the methane molecule, the two oxygen molecules, the one carbon dioxide molecule, and the two water molecules. And so these are just two different methods or ways to show the same thing occurring. But again, this is the traditional method. Notice also, and this is very important, that we have the same number of atoms of each type on both the left-hand side and the right-hand side of the reaction arrow. On the left-hand side, we have 4 hydrogen atoms. Right-hand side, we have 4 hydrogen atoms. See, there are 2 times 2, so there are 4 of these. Left-hand side, we have 1 carbon atom. Right-hand side, we have 1 carbon atom. Left-hand side, we have 4 oxygen atoms. 2 times 2 again. Right-hand side, we have 4 oxygen atoms. One other thing I want to point out, these coefficients right here, they indicate how many of these molecules we have. If you change the subscript on the molecule, what are you changing? Think about it. You're changing the actual identity. If we change this down here to a 4, now we would have 4 oxygen atoms stuck together, and that would be a very, very different molecule than these O2s. So pay attention to where the, if you're changing coefficients, if you can change coefficients, or if you're changing the subscripts, okay? But going back to the importance that we have the same number of atoms of each element type on the left-hand side, right-hand side of the reaction arrow. This is what's called the conservation of matter. Okay, so this is a law for chemistry, is that matter cannot be created or destroyed, and this will be true for all chemical reactions that occur during this semester. In our class, both the theoretical and the actual ones that are going